So maybe we can start. So I will start today with talking about discrete time Markov chain. And so the reference, a book by Norris. Then there is a book by Hagström. So I advise you to do the exercises of both. Then maybe there's a book by Friedman. And there is a book, the one by Levin, Paris, and Wilmore. So essentially everything I will say today, you can find it in one of these references. And so let's start with the definition. We have a space, which is E, which is a finite state space. So I will always assume that E is finite, though you can define it in countable state space. And the elements of E will be represented by X, Y, Z. And then we have probability space. So we have an abstract space omega, a sigma algebra F, and a probability which is defined on this sigma algebra. And we will say that a family Xn of random variables defined in this space, it's a Markov chain associated to a transition matrix P. So P here, it's a function from E times E to R plus. So which means that Pxy, it's non-negative. And so this for all xy in E. And I also assume that for all x, if I sum over y, Pxy, this is 1. So I'm giving, I have a finite state space. I have this transition matrix. So this I will call transition matrix. So I have this transition matrix, and I will say that this family of random variables defined in this space, it's a Markov chain with transition matrix P. If the following two conditions hold, first I will require these random variables to be on YouTube, you can ask. So maybe let me repeat. So those watching on YouTube, you can ask questions through the Google something. Google Classroom, yes. So if you have questions, you can ask questions in Google Classroom. Fine, so let me go back here. So I'll say that this sequence of random variables, it's a Markov chain associated to this transition matrix P. If the following two conditions hold, the first one, I will require, well, this Xn to be measurable. So by that, I'm saying that xn, it's a measurable random variable with respect to the sigma field. And then I will ask that for all n, that the probability that xn is equal to maybe say y, given that x0 it's equal to x0, xn minus 1 it's equal to xn minus 1. So for all n and for all x0, xn minus 1 y, the following hold, this is equal to p x0, xn minus 1 y. Okay, so, well, okay, the first condition, okay, it's just that these probabilities make sense because P is defined in the sigma algebra. And then the real condition is this one. It's, this is telling me that, well, if I know all positions of my process up to time n minus 1, and I want to compute the probability of the position at time n, well, this depends only on the position at time n minus 1, and it's given by the transition matrix. Okay, so this is the definition, which is quite simple. So, and of course, here I'm requiring these conditions for all events which make sense. So maybe here in the probability that x0 is equal to some y, it's equal to 0. Okay, and so since I'm not able to condition on events with probability 0, I'm not requiring this condition for this event. Okay, so it's implicit in this definition that, well, this is required only for sequences for which this probability is positive. Okay, so and let me give you maybe an example. Very simple one. So you have E, which is two-state, 0 and 1. And then you want to represent 0 and 1. So when, let's say that you're at 0, maybe you jump to 1 with some probability alpha, and maybe you jump to 0 with probability 1 minus alpha. And for 0, from 1 you go to 0 with probability beta, and you jump to 1 with probability beta, 1 minus beta. So here, alpha and beta are between 0 and 1. And so the way in which I will represent these Markov chain is that, well, I have P, which is this transition matrix. So I will just represent here, let's say that the probability that you jump from 0 to 0, and here the probability that you jump from 0 to 1, here that you 1 to 0, here 1 to 1. And so in my example, that would be you jump from 0 to 0 with 1 minus alpha, and 0 to 1 with probability alpha. And in the same way, you jump from 1 to 0 with beta, and 1 to 1 with probability 1 minus beta. So that will be my graphic representation. This is my matrix, and then I would require this object, this property, to be a Markov chain. Okay, questions? Yes?
Can you write a condition of maximum terms after independence?
Yeah, conditional independence. I will do that in a while. Yes, so we will show. So this is telling me that the present depends on the past only through the last step. And what I will show is that this is equivalent to say that conditionally on the present, the future and the past are independent. So future and past are conditionally independent given the present. But this I will show in a second. Okay, so here's first example. So maybe let me consider a second example. And before considering, let me just introduce a notation. I will call mu the initial distribution. Of the chain. So mu, it's a probability measure on E. And mu of x is just the probability that x0 is equal to x. So it tells me what is the initial distribution of this chain. Okay, just notation, mu, it's that. And my second example will be the following. I will construct a Markov chain from IID random variables. So let's say that I have a state space E, and I have a family xi0, xi1, which are IID. And so they are defined in some space omega fp. They are IID, so independent, identically distributed, and they take value in E. So they are E-valued. Okay? And now I have a function f from E times E to E. So I'm assuming that I have this family of IID, and I have this function, f. And I want to construct a Markov chain with these two objects. So I'll just define x0 will be xi0. So x0 will be xi0. And then I will define by induction, I will say that xn plus 1, it's equal to f of xi n plus 1 xn. Okay, and I claim that this is, so xn is a Markov chain. Okay, well, it's clear that they are, so we have to check these two properties. It's clear that they are measurable, okay, because, well, I'm assuming that these ones are measurable, and x, it's a function of these variables, so it's also measurable. So the first property, it's okay. Then I have to check the second one. So the second one is, well, I just have to write down what is the probability that, let's say, xn plus 1 is equal to y, given that x0 is x0, xn is equal to xn. Okay? Fine. But now, my first observation is that, well, x0, it's a function of f, not a function, not this one. It's a function of xi0. Well, actually, it's the identity. x1, it's a function of, well, xi1 and x0, but x0 is a function of xi0, so x1 it's a function of xi0, xi1. And by induction, I get that xn, it's a function of xi 0 up to xi n. What I want to say is that xj belongs to the sigma algebra generated by xi 0 up to xij. Okay, so this is the smallest sigma algebra which make xi 0, xi 1, xij measurable. So it's the sigma algebra generated by xi 0, xi 1, xij. Okay, so this is the notation I use. And what I'm claiming by, what I'm saying here is that xj, it's measurable with respect to this sigma algebra. Do you agree? Well, if you don't, you have to, okay? Make questions. Otherwise, I just go. So please interrupt me whenever you have questions. I'll be happy to answer. Fine. So, so this is an observation. These variables are measurable. So now let me go back here. Now xn plus 1, it's a function of xi n plus 1. So I will just replace, right, xn plus 1 in that conditional probability by its definition, which is f xi n plus 1 xn. So this is the probability that f xi n plus 1 xn it's equal to y, given that x0 equal to x0, xn equal to xn. Fine, I just used the definition. Now, I know that here I'm conditioning on xn equal to xn. So I can replace this xn by xn. So this is the same thing as the probability that f xn plus 1 xn equal to y, given that x0 is equal to x0, xn is equal to xn. Okay, because since I'm conditioning on this event, I can replace xn by xn. And now, this event here, all these random variables, they are measurable with respect to x0, xi 0, up to xi n. This was my observation. On the other hand, here I have a function which depends only on xi n plus 1. And these variables are independent. So this conditional probability, since xi n plus 1 is independent from xi 0, xi n, this probability, conditional probability, is actually equal to the probability that xn plus 1, xn, it's equal to y. Okay? And so this will be equal, well, xi n plus 1, it's identically distributed. So I can go one step further and saying that actually this is xi 0 xn equal to y. And this is what I will call my transition matrix. So this will be my definition of p x y, or xn y. Okay, so I will define P in this way. So let me check that P has all the properties I'm requiring. P here, it's positive. And if I sum over y, this gives me a sum here over y. Well, but f, when I take union over y, this gives me e. And this function takes value in e. So this probability is equal to 1. So indeed, P defined in this way, it's transition matrix, and I just proved the property of Markov chains for this transition matrix. Okay, so this indeed defines Markov chain. Questions?
So in this construction, you don't have like full representation power in the sense that there might be some transition matrices which you cannot represent using this construction.
No, that's the exercise I'm proposing. So now, what I propose as an exercise for you, it's, well, assume that you have a Markov chain. Okay, so let me write down the exercise. So exercise, assume you have a space E, which is finite, and you have a transition matrix P. Okay? So now I want you, so the problem is to construct xi, construct this sequence xi k, and construct a function f. So find a function xi, sequence xi, and a function f, such that if I define xn by this, I get a Markov chain with, on E, with transition matrix P. Okay. So any any Markov chain on a finite state space can be represented in this way. You just have to find the right function and the right variables. Okay, so this is an exercise. So questions up to now?
If you fix the initial distribution, you can still represent, or you'll be tied?
If you fix, then I will have to accept that xi0 has a different distribution than xi1. They won't be IID. They will be independent, but the distribution of the first one will be different. Any other question? Okay, so up to now, I defined Markov chains, and I gave you 2 examples. So now let's try to prove some properties of this Markov chain. So I want to keep the definition, and so the first property, lemma, maybe is that once you give me this, I can compute the probability of any trajectory. So what I claim is that what is a trajectory? Well, you tell me what is the probability that at time 0 I'm at x0, at time 1 I'm at x1, at time n I'm at xn. Okay. If you can compute this probability for any n, this is the probability that the process follows a specific trajectory. If you are able to compute that, you can compute anything. Okay, you can compute the probability that at time n I'm at some point y. I just compute all trajectories which end up at y, and I sum these probabilities. Okay? So my claim is that if I know how to represent this, I can represent any event for this chain. And what I claim is that this is equal. So I erased, but remember that mu represents the initial state, the initial distribution. So what I claim is that this is equal to mu x0 times p x0 x1 times p xn minus 1 xn. All right? So P is my transition matrix, and the way I read this is, well, this is the probability that I'm starting at time 0 from x0. Then I jump from x0 to x1, x1 to x2, until xn minus 1 to xn. Okay? So given mu and p, I can compute any probability. And, well, the proof of that, it's very simple. So maybe I know that by definition, the probability that x0 is equal to x0, this is equal to mu x0. Okay, so this identity holds for n equal to 0. And let's proceed by induction. So let's assume it's okay up to n minus 1. And now we want to get this formula for n. So what I will do is I will write this probability as the probability that xn is equal to xn, given that x0 is equal to x0, xn minus 1 is equal to xn minus 1, times the probability that x0 is equal to x0, xn minus 1 is equal to xn minus 1. Okay, so I'm just using elementary properties of conditional probabilities. Now, for the first term, I just use the property of Markov chain. So this probability that xn is equal to xn given all the past, this is just the probability that you jump from xn minus 1 to xn. And now, for the first probability, well, I use the induction assumption, and this is equal to mu x0, p x0 x1, p xn minus 2, xn minus 1. Okay, and this is exactly the formula I wrote. All right, so this proves the lemma, and therefore I have a very nice formula for the probability of the trajectory. Then the second property is the fundamental property of Markov chain, which informally tells you the following. If I know that at some time n, I am at some position y, starting from this time, what I observe in the future, it's exactly a Markov chain starting from the y, which means the following, that, so if I have a Markov chain xn, okay, and now I define a new process, y, let's say yk, I fix some m, and yk, it's x n plus k. Okay, so I observe my process starting from this time m, and I define a new measure, which I will call maybe P star. P star of an event A, it's the measure in which I conditioned on the fact that at time n, my Markov chain at time n, it's at x. Okay? So this is a new probability measure defined on my space. And what I want to say is that yk, for this measure P star, yk, it's a Markov chain with transition matrix P, and whose initial condition nu is just the Dirac measure at x. Okay, so suppose that you have a Markov chain, xn, and now I condition this Markov chain to be at x at time m. And I observe this chain starting from this time m. Okay? So you are at time n, and now you observe this chain starting from this time. What I'm saying is that given that you are at x, what you see, it's a new Markov chain with the same transition matrix and which starts at x. Okay? So this is the loss of memory, or if you want, so that if you know that at time m you're at some point x, what you see from this point on, it's a new object which is independent from the past. It's just a new Markov chain with this transition matrix P. So I want to prove, to show that yk, it's a Markov chain. So to prove that yk is a Markov chain, I have this first condition, but this first condition it's clearly satisfied because yk, it's xm plus k, which is f measurable. So all these variables are measurable. Okay. Do you agree? Okay, I started from an object which is measurable. So they continue to be measurable. And what I really need to prove is this condition. Okay, so what I have to show is that for this measure, P star, the probability that yn, maybe use j plus 1 equal to yj plus 1, given that y0 it's y0, yj it's equal to yj. And what I have to show is that this is equal to P. What I have to show is that this is equal to P yj plus 1. Okay. So this is what I need to show, and well, fine. So let's compute. I have a conditional probability, so I will write this conditional probability as P star yj plus 1 equal to yj plus 1, yj equal to yj, y0 equal to y0, divided by P star yj equal to yj, y0 equal to y0. Okay? So this is just definition of conditional probability. And now Now I will compute the numerator. And the same argument, and I will do the same thing for the denominator as well, but I won't write it. I'll just write for the numerator. So first thing I will use, what's the definition of this probability? This probability I'm conditioning to xm is equal to x. So this is equal to the same thing which is written over there, which is y. Okay, and maybe I'll just use that yj is equal to xm plus j. So xm plus j plus 1 equal to yj plus 1. Then the last one is y0, which is xm, given that xm is equal to x. Okay? So I can assume that y0 is equal to x, otherwise this is 0. Okay, so let's assume that y0 is equal to x. So now, well, what I can do, I know only what is the probability of a trajectory. So I have to write everything in terms of the probability of trajectories. So what I will do is I will write here as xm plus j plus 1 equal to yj plus 1, xm equal y0, which is x, and this is divided by the probability that xm is equal to x. Okay? I'm just writing that the conditional probability is the probability of the intersection divided by the probability. Então, y0 y0 é x. Y0 é x. Now, okay, this is a piece of a trajectory. So I have to express this piece of trajectory as the old trajectory. So what I will do, I will sum over all possible paths. So I'll sum over z0 up to zm minus 1 in E of the probability that xm plus j plus 1 equal to yj plus 1, xm equal to y0, xm minus 1 equal to zm minus 1, x0 equal to z0. Right? Because this probability I know. I have a formula for that. I don't have a formula for this one, but for this one I have a formula. Okay? And the same thing for this one. So this one, it's also a sum over 0, z1, zm minus 1 in E of the probability that xm is equal to x, and then xm minus 1 it's equal to zm minus 1 up to x0 it's equal to z0. Okay? And now I can use my formula. So now I can use the formula I proved in the previous lemma, which tells me that this is equal to mu z0, p z0 z1, p zm minus 1. Okay, let me write it x, because y0 is x, and then p x y1 up to P yj plus 1. Do you agree? Okay, so this is my previous lemma, and the same thing here. Okay? But now, when I'm summing over Z0, what I'm summing, it's I'm multiplying a line by a matrix. Okay, and let me understand this measure mu as a line vector, and I'm multiplying this line vector by a matrix. So this is mu P at Z1. Okay, it's the product of mu with P and computed at Z1. When I compute that, the second term here, it's PZ1, Z2. When I sum over Z1, what I get is that this line vector with this matrix, that will give me, okay. So what I claim is that if you sum over Z 0, Z1, Zm, mu, Z0, P0, Z1, P, Zm minus Zm x, that this is equal to mu P, and P appears here m plus 1 at x. So let me prove this formula by induction. Or maybe it's m here, maybe. So this is the power of P, okay? P to the power m. So if m it's equal to 0, this means that I'm just summing over Z0. Okay? And if I'm summing over, so if m is equal to 0, this means that I'm summing over Z0, mu Z0, and the last term, it's P Z0x, and this gives me mu P, okay, so here it's plus 1, mu P of x. Okay, so this formula is correct for m equal to 0. And let's prove it. Are you following, or is it? Sorry? Yeah. I'll prove it by induction, so I just prove it for m equal to 0. And then let's assume that it holds for m. And let's prove it for m plus 1. Okay, that I don't. Okay, let's erase the definition. So let's assume that it holds for m, and I'll prove it for m plus 1. So I want here it's m plus 1x. So now, if I sum for 0 to Zm, let me use, I assume that this formula is correct up to m, so I have these. So I'm summing first Z0 up to Zm, So now I'm summing at the end z over zm plus 1. When I'm summing, so maybe let me write. So when I'm summing these terms here, I'm summing up to m. So I have mu p m plus 1. And this is computed at the last term. So in our case, zm plus 1. And now I have here this line vector again, multiplying this matrix, and this will give me mu pm plus 2 at x. Okay? So this long but elementary computation tells me that this sum from 0 up to m minus 1 of this expression is mu. So I'm summing up to m minus 1. So I get m of the last term, which is x. Okay? And then I have these last terms. Px y1, p yj, yj plus 1. Okay? So this is from my formula. So I hope it's clear. And this sum gives me mu p m of x. Okay, so I'm computing the numerator. And now you see that this expression will cancel with this one, and what will remain is this. So what we proved is that this is equal to p x y1 p yj yj plus 1. See? So what we showed is that this numerator is equal to this product. Do you agree? Okay. Now, the difference between the numerator and the denominator is that I have one term less. So the same computation will give that the denominator is equal. So now I'm computing the numerator divided by the denominator, and this is equal y1 p yj minus 1 yj, and this is indeed equal to p yj yj plus 1. Okay, and so this proves that indeed this conditional probability is given by that, and therefore y it's a Markov chain, a new Markov chain. Okay. So if you know that at some time m you are at some point, you can observe the process starting from this time, and this is a new Markov chain with the same transition probability as the original one. And this is the Markov property. Okay, so I want to show you an application. time is it? There is no watch on the room. 9 to 6. So application, stopping times or hitting times. So let's say that I have a set A which is included in E, and I want to see the first time I hit this set. So I'll represent that by tau of A, and tau of A, it's the infimum over all n larger or equal to 0, such that xn belongs to A. Okay, so it's the first time I hit A. And let me represent by fk the sigma algebra generated by x0, x1, xk. Okay, so this is the smallest sigma algebra which make x0, x1, xk measurable. So it's the sigma algebra generated by this set, and this for k larger or equal to 0. And of course, fk, it's a family of increasing sigma algebras, and they are all included in F, because these variables are F measurable. And what I want you to observe is that tau A equal to k, so that this belongs to fk for all k. So the event that you hit the set A for the first time at time k, it's measurable with respect to fk. And why is that so? Because I can represent this set. Well, when is the first time that, when it happens that the first time you A, it's at time k. Well, this means that xk belongs to A, and you didn't hit k, A before k, which means that xk minus 1 does not belong to A, intersection, x0 does not belong to A. Okay? So you wrote this event as in terms of x0, x1, xk, which means that this event belongs to fk, and therefore this one belongs to fk. So this is just what I said. And this will be the definition of a very important object, which are stopping times. So I'll say that I have a function t from omega to n, union 0. So remember, omega, it's our absolute space. I'll say that it's a stopping time if it's f measurable, and if for all k, tau equal to k belongs to fk. Okay, so hitting times are examples of stopping times. Fine, so let's let me give you another example, which is a random walk in 0n. So I'm fixing n, and my state space will be the set 0 n. And I'm fixing a parameter p, which say strictly positive and bounded by 1/2. Okay, and now I consider the following Markov chain. If I'm at x, I will jump to x plus 1 with rate p, and I'll jump to x minus 1 with rate 1 minus p, which I will call q. Okay, so if you're at x, you go to x plus 1 with probability p, x minus 1 with probability 1 minus p. And when you hit n, let's say that you stay at n, and when you hit 0, you stay at 0. Okay, you can think that this is a game, and the position is the amount of money you have. And now I have t, which is the hitting time of the set 0 n. Okay. When you hit 0 or n, the game ends, and either you lost all your money or you won the jackpot. But of course, p, it's bounded, it's less than 1/2. So unless p is equal to 1/2, this is not a fair game. So my first problem is to show that, well, you hit 0 or n in finite time. So I want to show that given that at time 0 you are at x, you hit either 0 or n with probability 1. Okay? And to simplify notation, I will represent by px the probability, which is the conditional probability that at time 0 I'm at x. Okay, so this is, when I put here x, it's just that I'm conditioning to be at x at time 0. And so what I want to prove is that starting from x, I will hit either 0 or 1 for all x. Whatever position I start, I hit 0 or n in finite time. So how you prove that? So the idea will be to use the Markov property. And so let me define f of x as this probability. So I'm defining this function f, which computes this probability. And what's clear is that I know its value at 0, and I know its value at n. And at 0 and at n, its value is equal to 1. Right? Because if I'm starting from 0, I hit 0 at time 0. Same thing at n. Now, the way in which I will prove this, it's I will obtain an equation for f. So let me take x different from 0 and n. So I'm starting from x, and what I observe is that if I start from x, the event tau it's finite, it's a function of x1, x2, and so on. Okay, because tau, what I want to say is that it belongs, when I write that it's a function, what I'm writing is that this belongs to the sigma algebra generated by x1, x2, and etc. Okay, because since I'm starting from x different from 0 and 1, tau cannot be equal to 0, and therefore this event under this probability measure can be written as, well, either x1 belongs to this set, so let me call the set 0, let me call the set 0 and the set B, x1 belongs to B, or x2 belongs to B, or x3 belongs to B, and so on. So it's indeed an element of this sigma algebra. Now, this is what I want to compute, and I will investigate this probability according to my first jump. So what happens at time 1? Well, let's sum over all possible values. Okay, so this is a tautology because these events are disjoint, so the sum of these probabilities is probability of the union, and if we take the union, this is everything. But according to my definition, if I'm at x, at time 1, I'm either at x plus 1 or at x minus 1. And what I will do is I will condition this event on x1 equal to y. So this is the sum of tau less than infinity, given that at time 1 I'm at y, times the probability that at time 1 I'm at y. Okay. Now, this object, as I claimed, belongs to what happens after time 1. Okay. And what we proved, the Markov property tells us that conditioning on the fact that at time 1 I am at y, what happens after that, it's like a Markov chain, which at time 0 starts from y. So this probability here, by the Markov property, it's equal to the probability that I'm starting from y at time 0, and I want to compute what is the probability that I will hit 0 or n. Okay, what's very important here is that this event depends on the future, depends on what happens at time 1, 2, 3, so at times after time 1. Okay, because this was the identity we proved. We proved that if I compute any event after this, the time n, m in our case, here time 1, then I can use the Markov property to say that this is. And therefore, if you accept, okay, you have to think a while to accept this identity, but this is exactly the Markov property we proved. Because if you want to write it in all details, what you do is you write this like that. So what is this event? Is the event that at time 1 you hit set B. Union, well, but you want to use the additive property of the probability, so you want to rewrite this expression not as I wrote here, but in terms of the joint unions. So this means that I want to write this event as either a hit 0 and 1 B at time 1, or I didn't hit B at time 1, but I hit it at time 2, or I didn't hit time 1, 2, but I hit it at time 3, and so on. So I can write this event as this countable union. Now, this countable union becomes a sum. Now I apply this Markov property and bring back, and I get, again, my event tau is finite, okay? So think a bit about, I wanted to give you this example exactly to understand what's the meaning and how you apply, how you use this Markov property, okay? So it's here. And if you accept that, now I have an equation for f, okay? What this identity is telling me is that f of x, it's equal to this sum. So here I have f of y. This is f of y. Multiplying this probability, but as I told you, here the sum actually runs only over two terms, either x plus 1 or x minus 1. So you jumped from x to x plus 1 with probability p. So you get p times fx plus 1 plus q times fx minus 1. And so you have a sort of differential equation for your function f. Okay, so I will rewrite this equation in the following terms. So remember p and q, p plus q is equal to 1. So let me subtract fx on both sides to write this equation as p fx plus 1 minus fx plus q times fx minus 1 minus fx equal to 0. So mind if p is equal to 1/2, what you get here, it's the discrete Laplacian. So you get that the discrete Laplacian of f is equal to 0, and you have the boundary conditions that f at 0 it's equal to f at n, it's equal to 1. Okay, so in the special case in which p is equal to 1/2, the fact that the discrete, let me represent by delta the discrete Laplacian, that delta f of x it's equal to 0, and this equation here holds for x between 1 and n minus 1. So you get that the discrete Laplacian is equal to 0, which means that f it's linear, and f it's linear, but the boundary values at 0 and 1 and n are 1, so you get that f it's constant equal to 1, which is what we want. Okay. Still, you have to show that f it's linear, but it's easy. But let's see how you prove that f it's equal to 1 for p smaller than 1/2. Okay, so let me show you. So what I will do is I have this equation. I will multiply it by 1 minus fx mu x. Okay, so what I know is that 1 minus f of x, so it follows from this equation that 1 minus fx P mu x fx plus 1 minus fx plus 1 minus fx q mu x fx minus 1 minus fx, and this is equal to 0. Okay, I didn't tell you what mu x is. I'll tell you in a while. And well, okay, it follows from that this equation holds for x between 1 and n minus 1. So this is equal to 0. So I'm allowed to sum from 1 to n minus 1. Okay, so I get that this sum is 0. And now I will play around. I will here change. So I'll call x plus 1. So this implies that 0, it's equal. I have still the first sum. I do not touch this first sum. But I'll change variables in this second sum. So I'll call x to x plus 1. So instead of running from 1 to n minus 1, I will run from 0 to n minus 2. Okay? So plus the sum from 0 to n minus 2. And what I get here, it's 1 minus fx plus 1 q mu x plus 1. Yes? Okay, so this is what I get by changing my variables. And now I want this to be equal to that. So I'll choose because you see I have the same term here. I have fx minus fx plus 1, which appears there. And there I'll get this with the minus sign with that. I'll get a square. So I want q mu x plus 1 to be equal to p mu x, which means that I want mu to be mu x plus 1 mu x to be equal to p over q. So I define mu by this formula. Okay? I fix mu 0 to be 1, and then I define mu x plus 1 mu x by this relation, so I get mu x. And now I want, so this, I can replace that by p mu x, which is what appears in the first sum. So this one is running from 0 to n minus 2, this one from 1 to n minus 1, so I have boundary terms. So I have one boundary term, which is here, coming from 0. So let me write that one. So x equal to 0, so p mu 0, 1 minus f1, and f0 minus f1. Let me write, so this is the boundary term at 0. I have a boundary term at n minus 1. So this is p mu n minus 1. Then I have 1 minus fn minus 1. Fn minus fn minus 1. And now I have the terms between 1 and n minus 2, p mu x. Okay, so here I have fx plus 1 minus fx. And this is multiplying 1 minus fx. And here I have minus this term. So minus 1 plus fx plus 1. Okay. And this is okay because now I know that f0 and fn are equal to 1. So f0 it's 1, And these terms is positive. Because the first term, it's p mu 0, 1 minus f1 square. Then fn, it's also equal to 1. So the last term, it's p mu n minus 1, 1 minus fn minus 1 square. And all these terms are fx plus 1 minus fx square. So plus mu x p fx plus 1 minus fx square. And this is equal to 0. Okay. And since it's equal to 0, all terms are positive, they are all 0. And this tells me that fn minus 1 is 1, f1 is 1, and the difference are, so f it's constant. So f it's constant equal to 1, even in the case in which p it's less than 1/2. Okay? So this is a usual trick in order to prove uniqueness of these type of equations. Okay, questions? So, okay. The second part, which is this computation, is just for you to know how to prove a uniqueness of certain elliptic equations and one-dimensional. But the important part in this computation was the use of the Markov property in order to get an equation for f. Okay. So this is was the application. Now, but okay, to show that the heating time is it's finite almost surely, it's not very exciting. What we would like to compute is what is the probability that you will lose all your money or you will win the jackpot. So what we are really interested in is, now that we know that at some point we'll hit either 0 or n, what you would like to compute, it's say what is the probability that you hit n before you hit 0. Okay, now what changed in this computation? Well, the boundary conditions are now different, because if you start from 0, this probability is 0. If you start from n, it's 1. So you have different boundary conditions. f0, it's equal to 0, and fn, it's equal to 1. But now I can just repeat my argument. So let's call this event, let's say D. So D is the event that tau n is smaller than tau 0. And this is what I want to compute. So let's take x different from 0 and n. And let's again divide this event according to the first jump, the position of the first jump. Now let's condition that on x1. So that didn't change. And now I can argue again that D, which is the event that you hit n before you hit 0, if you start from a point which is not 0 and n, it's something which depends on time 1, 2, or etc. Which means that I can again use the Markov property to claim that the probability that of the event D, given that at time 1 I am at y, this is the same thing as start your process from y and compute the probability of the event D. And so I get the same equation for this new function, just that the boundary conditions are now different. So now the boundary conditions are that at 0, f is equal to 0, and at n, f is equal to 1. So what you have to do, you have to solve this equation. And by solving this equation, you get the value you're looking for. And again, if p is equal to 1/2, what you get is that the Laplacian is 0. And from the Laplacian being 0 with these boundary conditions, what you get is that fx it's now equal to x over n. Okay, it's linear, and at 0 it's 0, and at n it's equal to 1. So you get for p equal to 1/2, well, just check that this is indeed the solution, and then I leave it to you to try to compute the solution of this equation when p is different from 1/2. What you have to do, you have here an equation for the difference. So you solve the equation for the difference, and once you solve this equation, you get, by using the boundary conditions, you get the correct values of f. So this gives you, what I'm saying is that this is equal to 0. So if I take out this piece in the other way, I'm saying that fx plus 1 minus fx, it's equal to fx minus 1. So let me call this hx. You get that hx it's equal to hx minus 1 multiplied by q over p. So you iterate this expression, and you get that hx it's equal to this ratio q over p to the power x times f1 minus f0. Okay? So you can express all difference fx plus 1 minus fx in terms of f1 minus f0. With this, and the fact that fn minus f0 is 1, you get, you can get the values of first the difference fx plus 1 minus fx, and then the value of fx. Because once you know that fx plus 1 minus fx is equal to something, you just sum over, and you use that fn minus f0 is equal to 1. Okay, so do that as an exercise, and then if you are not able to find, we discuss it here. Okay, so this is an application, but this is the important point. So this is how we are going to use the Markov property, right? So fine. Okay, so everything works the same, but your equation will be more complicated, so you won't be able to solve it as I'm proposing. And I don't see how you can solve this equation. So what you'll do is you'll prove that there exists a solution, that the solution is unique, but you have no idea of how, you don't have a closed formula for the solution. you could ask the same thing for if you take in higher dimension. Okay, so in higher dimension, you won't have closed equations, closed formulas for the solution of this equation. You could think that instead of working in one dimension, you have a two dimension, and say that in this two dimension, you jump to one of the four neighbors with certain probabilities, and you do that until you hit the boundary, like we do here, and you have a value at the boundary. And also in that case, you won't find. I mean, you can do everything as the same, so you get an equation, but you can't solve this equation. Okay, so maybe since, what time is it? 27. Okay, so maybe since you asked this question, okay, so let me take this opportunity to discuss this problem. So now I have a discrete Laplacian, let's say in 2 dimensions, but everything I'm saying it's any dimension. And I have a differential equation, a discrete differential equation. So I want to find the solution of Laplacian f is equal to 0. So let's say that we are working on a square or a cube, 0n. And I want, so this is my cube, lambda n, which is 0 n square. I have a boundary of lambda n, so these are the elements of x in lambda n for which there exists y not in lambda n, such that x minus y is equal to 1. Okay, so the boundary are these points. Okay, so these are all points in lambda n for which there exists a neighbor which is not in lambda n. Okay, because this point here has a neighbor here, this point has two neighbors. And let me define the interior of lambda n, which is set lambda n minus the boundary. So I want to solve this equation for x in the interior, and I want f of x to be equal to g of x for x at the boundary. So I fix a function g at the boundary, and well, in continuous, that will be called the Poisson equation. Okay, you have Laplacian equal to 0 at the interior, and then f equal to some function g at the boundary. And you want to solve this equation. Okay. So now, what I want to use what I just presented to you, not to solve this equation, but to propose a representation of the solution of this equation. So what I claim is that, okay, take xn, a Markov chain, which when it's at x, it jumps to one of the neighbors with probability 1/4. Okay, choose one of the neighbors, jump there to 1/4. This defines a Markov chain. So this is the transition matrix. And when it hits the boundary, you do whatever you want. I don't care. But say that if you are at the boundary, you have 3 neighbors, so you choose one of them with equal probability and you jump. So with probability 1/3, here you probability 1/2. But you can do whatever you want at the boundary because that will not enter into my argument. Fine, so it's clear what the Markov chain xn is. And what I claim is that now I can define tau as the hitting time of the boundary. So this is the first time that xn belongs to the boundary of lambda n. Okay. So you prove that the heating time is finite with probability 1. And what I claim is that the solution of this equation, fx, it's given by, well, you start your Markov chain at x. Ex will be the expectation with respect to px. This probability I defined below is the probability of the Markov chain which starts at x. So Ex of g x tau. So time tau, it's the first time you hit the boundary. So at this time you are at the boundary. So x tau, it's a point at the boundary. So g, it's well defined. And what I claim is that the solution of this equation can be represented by these expectations. And why is that so? Well, first, if you start from the boundary, the heating time is 0. So this is just g of x0, g of x. So f is equal to g at the boundary. Exactly as we did before. Okay? And now to show that f satisfies this equation, I will just repeat the computation I did over there. So, but now instead of probabilities, I have expectations. So I want to compute the expectation of g x tau. I take a point x, which is not at the boundary. Since x is not at the boundary, the heating time is larger than 1. Will happen after time 1. So I will write my expectation according to the possible values of the Markov chain at time 1. Okay? Now, I condition that on the fact that at time 1 you're at y. And again, I use the Markov. Since this event depends on the future, I can use the Markov property to say that since I know that at time 1 at y, this is like starting a new Markov chain at time 0 at y and computing this expectation. So this is fy, and so I proved that fx is equal to the average of fy according to this probability. But these probabilities are all equal to 1/4. So this is telling me that fx is equal to the average of f around x. And this is exactly this equation. Right? Laplacian, it's 1/4 f sum over the neighbors of fy minus fx. So this, exactly the same argument, gives me a representation of solutions of differential equations. All right? Okay, so maybe we stop here today, and then tomorrow I will continue with these properties of Markov chains. Questions? Okay, so we continue tomorrow.